So our next definition is about the continuity of a vector value function. We say a vector value function R of t is continuous on at point at a, t is equal to a, if we are having here limit r of limit t tends to 0, the limit of this function t tends to a, r of t is equal to r of a. Then we say the limit is equal to value of the function. If limit is equal to value of the function, then we say the function is continuous. And if limit is not equal to value of the function we say is not continuous. If this is continuous on each point a in the interval I, then we say this is continuous on interval I. We take as a note, if r of t is continuous at each t a in the interval I, then we say that the function r of t is continuous on interval I. So that's the idea. Here is this continuous at one point, then this is continuous for all values on A. So here is the continuous at the point at each point A, then it's continuous in the interval. So that's the idea we are having here. We can have now extend this one, and we can have the definition of the derivative. This is our derivative of the function. This third definition we are going to have here. Definition derivative of the function. It's just like as we had done before in our previous courses for simple function. Now we discuss for the vectorial function. So we say we having here the function f r of t is equal to f of t I plus g of t j plus h of t k is a vectorial function on certain domain, and these are the components are the components f of t, components f of t, g of t and h of t are differentiable. Then we say, and then we can write here the derivative of the function d by dt of r of t is equal to, I just change the color, is equal to d by dt of f of t I plus d by dt of g of t j plus d by dt of h of t. Okay, that's we take the component of each of the function by using this one. So we have a component derivative of the component f of t, derivative of component of g of t, and the derivative of component of h of c. So we can define derivative for each thing. We can write also, this is here, we can take the other notation. We write here dash, that's means the derivative, and this here is f dash of t, g dash of t and h dash of t. We can use also this notation for writing the derivatives. We are using the notation with I, j and k. We can use the bracket, and you can use this notation. Function we say here r of t, derivative of function r of t. So we are having certain results which are being related to this one. We take this as, for example, our note 1. Then, for example, I just make the diagram for that one. This is my y axis, this is my z axis, this is my y axis, and this is my x axis, origin, y axis, and z axis. And I am having here the curve. My curve is this vector value function shown this curve. Now if I want to define my a function r of t. So say I may define my function r of t at this point. This is my function r of t. So when I say I want to find the derivative of the function, so my derivative of the function in this case will be here is my function r of t, r of t. So when I define my derivative of the function, so my derivative of the function is this one, is tangent to the curve. This is my r dash of t. So if I want to liberate it further, then this is geometrically I am showing that one. This is my r dash of t. I can just define this one further. I'm having here z-axis, I'm having here y-axis, I'm having here x-axis, origin y-axis, z-axis, and this is my curve. I make it a little better than this one. So this is my curve, and this is my r of t. Here is my r of t. This is my r of t, and here I am having here, this one is my r of t plus delta t. T is my independent variable. So here I can get this one, and this one is here is, this value is r of t plus delta t minus r of t. When we want to find the our definition, then dr by dt you can say is equal to the limit delta t tends to 0 r t plus delta t minus r of t over delta t. So that gives me the derivative of the function. That's my definition for that one. And here r of t we are having x, y, and z. So f of t, g of t, h of t. So that gives me similarly as I defined above. This is my node 2. This is my node 2. Now I can have here more ideas related to that one. That here, for example, now if I am defined here this r of t, so I can just show it. Then this is my r dash. Then this is going to 0. So this is my r dash of t. Then r dash t, we say here node 3. Node 3, I say node 3. I say that my r dash of t, the vector r dash of t is called tangent vector. Is called tangent. We have the idea of the tangent already defined when you have the derivative for a function f of t, y is equal to f of t, we say f of x, then we have dy by dx is tangent to the curve. So similar to that, when dr by dt is r dash of t, that is tangent to the curve. The curve is defined by f of ti, g of t, j, h of t, k. We are having the vectorial function, but this r dash of t will be tangent to the curve at any point of the curve, to the curve at point P. I take this as point P, and I take this point as point Q. So here when I say this delta t tends to 0, then our point Q is moving to point P.